Bookkeeper 1.2, displaying quantitative data with graphs. Alright, so one of the simplest and easiest types of graphs that we can make is a dot plot. We'll use this even though it's so simple. We'll use it all year long because it still tells us a lot about the data, and it's a really easy way to categorize and organize your data. So the way that we make a dot plot is first we draw a horizontal axis, like the x-axis or a number line, and we label it with the variable name. Remember, you have to have your labels. Alright, then we're going to scale that axis from the minimum to the maximum value of the variable. You want to have nice even increments. You don't want to skip around. You can skip 5, 10, 15, 20, but you wouldn't do like 5, 20, 22. Like, you want to make sure it's nice and even. And then you want to make your dot above the location on the axis that corresponds to each data value. Very easy. So for example, here we have the number of goals scored per game by the 2004 women's soccer team. So I'm going to create my dot plot by creating a horizontal axis down here. And I split up my dot plot nice and even, so I have 0, 1, 2, 3, 0, 1, 2, 3, 4. You don't have to skip the way they skipped, but you can definitely do it to spread your stuff out a little bit more. Notice that I also labeled my horizontal axis number of goals scored, and then I placed my dots. So for here, for 0 goals scored per game, I see that there's 1 dot. That means only one time did they not score at all, which I can see that in the table. Where for like 1 goal scored, I see that's the highest. So that happened 1, 2, 3, 4, 5, 6, 7, 8. And if I go to my table, I should also be able to count 8 ones to represent the 8 times that they scored 1 point in the game. Alright, so the purpose of the graph is to make the data easier to understand and easier to read. And any graph that we make or any graph that we look at, we're always looking for the overall pattern of the graph, and then we look for any like striking departures from the pattern. So we look for the pattern, and then we look at anything that's like not of the pattern, that's thrown off from the pattern. So to describe the overall pattern, we use what we call SOCs. So we look at the shape, the center, the spread, and then any departures from the pattern is what we call outliers. Again, the way that we remember that and what I refer to it as from here on out is SOCs. Again, that's shape, outlier, center, spread. Alright, so on page 28 of your textbook, we have an example that shows us the estimated gas mileage per different types of cars in 2009. Alright, so again, the variable is your model. The individuals is the model, and the variable is your mileage per gallon. We have our dot plot that was already created for us that represents the variable or the distribution of the variable. So if I wanted to describe my data, so I want to do my SOCs, I want to describe shape, center, spread, and any possible outliers. I would simply look at the data and just say what I see. So for shape, I would say something like, in the dot plot, we can see that there are clusters of values. We see clusters around cars that get 25 miles per gallon. We see clusters around cars that get 28 to 30 miles per gallon. And we see clusters around cars that get 33 miles per gallon. We can also look at the gaps that we see. So we see gaps between the Acura RL, which is 22 miles per gallon, the Rolls-Royce Phantom, which is 18 miles per gallon, and then the Bentley, which is 14 miles per gallon. Now for center, I could say something like the median is 28. This is the typical value, so that means that the typical model year 2009 midsize car got about 28 miles per gallon on the highway. For spread, I could say something like the highest value is 33 miles per gallon and the lowest value is 14 miles per gallon, or I could just simply say that the range is 33 minus 14, which is 19 miles per gallon. We haven't learned how to calculate outliers, so what you would say is that it seems like there might be 2 possible outliers at the Bentley, which is 14 miles per gallon, and the Rolls Royce, which was 18 miles per gallon. These are potential outliers. We didn't actually calculate to see if they are outliers yet. Once you learn how to calculate it, you'll no longer say potential. You'll tell me whether it is or not. Now, notice I kept saying I would say or I could say. What I say is not exact. It's kind of like your own interpretation of the data. Just make sure it makes sense, and stuff like the center, you want to make sure you actually calculated that correct. If you say the median value is, that's the middle number, versus if you say the average is, now you actually have to calculate the average. So you want to be careful how you say it, but it doesn't have to be exact. It doesn't have to be exactly what I say. It can be worded differently as long as you get all four of the categories or all four of the elements of socks. All right, so specifically when we're looking at shape, what you want to look for is symmetry or skewness. What you usually say is when we look at a graph, if you think it's symmetric, now remember, nothing in real life is actually symmetric. Like, you don't see something that's like perfectly symmetric. So what we say is that the distribution is roughly symmetric. Sorry guys, hold on. All right, so the distribution is roughly symmetric, which means that the right and the left-hand sides of the graph are pretty much mirrors of each other. They're not exact, but they're pretty much mirrors of each other. Now, we can also say that the distribution is skewed right, which means that the right side of the graph is much longer than the left side, or skewed left, which means that the left side of the graph is much longer than the right side. Now, for skewed right and skewed left, the easy way to remember it is to look at your feet. Your right foot is skewed right and your left foot is skewed left. So for your right foot, if you're looking down to your right foot, you see that your little toe is real short, that's on the right hand side, and your big toe is really big, that's on the left hand side. That is what skewed right should look like. And skewed left, again, should look just like your left foot. The little portion should be on the left side and the big portion should be on the right side. Alright, so here's three graphs. The first one is, again, it's not perfect, but it is roughly symmetric. The second one, I see the tail over here. The tail over here is on my left-hand side, and that definitely looks like my left foot, so I'm going to say that's skewed left. And over here, I see the tail is to the right-hand side. It looks like my little pinky toe would be over here, and my big toe would be over here, so that's going to be skewed right. Alright, so again, when we compare distributions, you want to remember socks. So let's do another example to make sure we truly understand that. So if I look at example 32, or example on page 32, we're looking at the household sides of the UK versus South Africa. Now, if we want to compare these, again, this is not exact. You don't have to say exactly the same way that I say it, as long as you put in the elements of your socks and you're good to go. And guys, also don't be afraid to actually say shape, center, like, you want to go ahead and make sure that you're being very clear that you're saying those things. You don't want me to have to guess or find where you possibly were talking about shape. You want to go ahead and outline that in your writing. So for shape, I could say something like the distribution of household size for the UK sample is roughly symmetric and unimodal, while the distribution of South Africa, or the South African sample, is skewed to the right and unimodal. For center, I could say household sizes for South African students tend to be larger than the UK students. The median household size for South Africa is 6, where the median household size for the UK is 4. For spread, I could say that there's more variability in the household size for South African students than for the UK students. The range for South Africa is 23, where the range for the UK is 4. And then for outliers, I could say something like there doesn't seem to be any potential outliers in the UK distribution, but there are 2 possible outliers in the South African distribution on the right tail, which would be students reported 15 and 26 people living in their household. Now, again, remember that doesn't have to be exact. You're just kind of stating what you see, going through what you see, and putting that down. And again, for your outliers, you don't want to say they're definitely outliers. You can't say they're definite unless you calculate it. All right, another type of graph that we have is a stem and leaf plot, or a stem plot. It's a really nice way of organizing your data and also seeing the shape. It's pretty much just a dot plot turned on its side. All right, and it uses numbers instead of dots. So how we make a stem and leaf plot, the first thing we do is we separate each observation into a stem, which is all numbers but the final number, and then your leaf, which is just the final number. So we write down all possible stems. We write down all possible stems from smallest to largest in the vertical column, and then we draw a line, and on the right of that we write down all the leaves. So on the left we have our stems, and then on the right we have the leaf. You always want to arrange your leaves in increasing order out of the stem, and then again, just like with your bar graphs, you want to make sure you have a key that explains what the stems represent. All right, so here we're going to look at the 20 female AP Statistics students who were asked how many pairs of shoes do they have, and we're going to construct a stem plot. So we're going to separate each observation into a stem, which consists of all but the final digit, and a leaf, which is the final digit. We're going to write the stems in a vertical column from smallest at the top to greatest at the bottom, and then we're going to draw a vertical line to the right of our stems. Remember, you do not want to skip any stems. Even if there's no data for that particular stem, you don't want to skip it because you want to see those gaps and those holes. All right, so once we have our stems down, we go ahead and add our leaves, which is the last digits. Now, you want to remember that here we just put down exactly what we saw. So for each stem of 1, we put down like each of our leaves. So like here is 1 and then 9, or 1 and then 3, or 1 and then 3 again. So you want to put that down. But you have to remember that you need to go back. Sorry, guys. So you want to go back once you put your leaves in there. You want to go back and actually put them in increasing order out of the stem. So you wouldn't leave it like this. You want to go back and put it in so that it's getting bigger as you go further out of the stem. Now again, what this represents is 1, 3, 13, 13, 13, 15, 19. That's what it represents. Now we know that's what it represents, but the reader or the audience that you're presenting this to wouldn't necessarily know what that means. So you want to include a key to say something like 49 represents 49 pairs of shoes, so that people know what you're talking about. Because again, it doesn't necessarily have to mean 49. It could have meant 4.9, or it could have been 4,000. I mean, it could have been anything. And so you want to be really clear by providing your key. Now, we also could do what we call a splitting stem. A splitting stem is used when you have a whole bunch of data values that are really bunched up together, or when you have a smaller data set. It helps you to better see the shape of the data. So a splitting stem, so here's our data set. A splitting stem, instead of saying 0, 1, 2, 3, 4, 5, I do 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5. I'm splitting it up. So this first 0 represents 0, 0 to 0, 4, and this would be 0, 5 to 0, 9. This one would be 1, 0 to 1, 4, and then 1, 5 to 1, 9. So I'm kind of splitting it up so that all of the zeros are together. The first set of zeros would be in one piece, and the second set of zeros would be the second piece, and so on and so forth. So for example, males, I can do like this male had 4 pairs of shoes, then we had 5, 5, 5, 6, 7, 7, and so on pairs of shoes. We split it up so that we could see the difference between the lower zeros and the higher zeros, if that makes sense. And again, we'll look at examples of this, more examples, and I'll have you create some of these in class when you come in tomorrow. Now, we also have what we call a back-to-back stem plot, where instead of just having males, we can compare males and females. So for instance, for this example, I put the males on the right hand side, but you can include another set on the left hand side of your stem. So here we can put in females on this left hand side, and again, we're going out of the stem as we're getting larger, we're going out. So I can make a comparison. For instance, the center of the males seems lower than the center of the females. There's more variability with the females than it is males, and it looks like we have a couple potential outliers with the males. We can see that when we do a back-to-back stem plot. We can actually compare the data set. Oh yeah, and don't forget, you really need to make sure you put your key. If you don't put a key, taking off points every single time. So make sure you guys have your key. Even if it's kind of obvious what you're doing, you still want to include a key, just because that's the proper way to create a graph. All right, the next type of graph we have is our histograms. It's one of our most common types of graph that we use. The way that we make a histogram is we divide the data into classes or bins. If you're using like Excel or something like that, they call it bins, but it's classes of equal width. So categories are groups of equal width. You want to find the count or the percent, so your frequency or your relative frequency of each individual in each class. And then you want to label and scale your axis to draw your histogram. Remember, the widths of the bins or the classes have to be equal. The height of the bars is the frequency or the relative frequency, and your bar should touch, all right, unless you have a gap in your data set. All right, so we have on page 35 some more data of residents from each state who were born outside of the United States. So you see here, this is the count, or the percent of people that were born outside. So from 0 to 5%, there were 20 states. So the count is 20 states that had 0 to 5% of the people born outside of the United States. Or there were 13 actual states who had 5 to 10% of the people born outside of the United States. We total out here at 50, which makes sense because there's 50 states. So we're accounting for each and every state to figure out what the percentage of residents who are born outside the United States are. Notice the purpose of making a histogram in this case is because we're looking at ranges from 0 to 5%, from 5 to 10%, from 10 to 15%. So we're looking at ranges, and that's what's making it appropriate to use a histogram. So for the histogram, we have the number of states. We're using counts here, so number of states. On our y-axis, and on our x-axis or horizontal axis, we have the percent of foreign-born residents. All right, so then I just put in my data values, making sure that my bars touch, and I create my histogram. Now here we can see this data set is clearly skewed right, meaning that there are very few people or few states that have more than, let's say, 25 to 30% of the residents who are born outside of the United States. I mean, you could tell a lot from a histogram. We can go into more detail if we wanted to, because we could analyze it using SOCs to talk about the center, the spread, the shape, the outliers, and so on and so forth. Now, you want to make sure you use your histograms wisely, because we will make a lot of histograms in this class. You don't want to confuse a histogram with a bar graph. A histogram touches, a bar graph doesn't. All right, a histogram will show you the shape a lot better than the bar graph will. And not only that, your histogram is broken into classes or bins or groups where your bar graph is not. You want to use percents instead of counts on the vertical axis if possible. When you're comparing distributions that have different number of observations, if you weren't comparing two different distributions, or you had let's say the same number of observations, you could use counts, but generally we try to use percents. And then just keep in mind that just because a graph looks pretty, it's not necessarily meaningful. Like, you could put let's say a bar graph, or create a bar graph, that might not be as meaningful as if we had done a dot plot, or I don't know, stem leaf plot. So you want to make sure you use an appropriate graph. In other words, a lot of times you'll go to workshops and see different data being displayed, and the data is not meaningful because they didn't use the right type of graph. So you want to make sure you're using the right type of graph to get your point across.